bending and shear stresses in beams. So here you will get 20 marks question. In this, we have a derivation and followed by problems. So we'll start with this bending stress and shear stress in beams. So you know bending. Okay. Bending stress is the one where which is induced due to the bending moment. So due to the application of the moment, the beam is going to bend. So due to that effect, the stresses induced, we call it as a bending stress. Just for an example, if you hold a rubber in a finger and you are going to apply the forces at the end, it is going to sag or it is going to hang, right? Hug. So that one of the surface of the rubber is being tension. If it is a sagging, if you are bending the rubber in the sagging manner, that is in this manner, the top portion will be in compression or the bottom portion will be in tension. So if you are going to bend in this manner, the top portion will be in tension and the bottom portion will be in compression in the hogging bending moment, right? So here the concept is, the next concept is theory of simple bending. So for example, if you consider any beam, it is some cross section of the beam, right? So it is before the application of the moment. So this is the beam section, this is before application of the moment. So if you consider any beam, there will be an axis that we call it as a NA or a neutral axis. So at this neutral axis, we call the name by neutral axis for a beam, where the stresses will be zero at this neutral axis. The stress for the beam will be zero at the neutral axis before applying the load and also after applying the load. The stress at the neutral axis will be zero. So now we consider this beam. So some section of the beam is considered, that is EFGH, right? So there is some certain portion AB of the beam is considered, which is at a distance y from the neutral axis. So here for this section. So when the moment is applied at the end, so we are going to apply the moment at the end of the. So after the application of the moment, bending moment, the beam is going to bend in this manner. So the angle of bend, that is theta for the beam. So when the beam is bending in this manner, the length AB is the cross section what we considered, it is going to be increased in length, whereas CD is the neutral axis. Since the stress of the neutral is zero, the CD length will remain the same before and after the application of the moment, a bending moment. So the concept of theory of simple bending, whenever moment is applied or bending moment is applied on the beam is going to bend in such a manner, either it is going to bend in a hogging manner, this is a hogging moment, or if it is a reverse, the beam is going to bend in the sagging moment, such that in a hogging moment or a sagging moment, the stress at the neutral axis will be zero. Whatever the moment that is applied, the beam is going to bend in a hanging or sagging manner. The stress at the neutral axis will remain zero. If the beam is bending in this manner, what it is shown here, it is a hugging moment. The top surface will be under tension. The bottom surface will be under compression. If it is a reverse, it is a sagging moment. The top surface will be in compression and the bottom surface will be in tension. So that is a theory of simple bending. If it is a statement, you need to write the sketch. So before the application of the load and after the application of the load, and you need to explain. So that is before the application of the bolt, all the fibers are in parallel. So if you take any line along this section, along the beam, that is HE is a section, right? All these coincide with each other. There is no angle of twist is measured, that is theta is not there here. So when the moment is applied, the beam is going to bend in this manner. The H is going to shift. So there is an increase in length. HG is shifted to H dash G dash. Similarly, F is shifted to E dash F dash. So in this case, E dash F dash is decreased in length, H and G are increased in length, right? And you need to remember that this is the neutral axis. NA is the neutral axis. So after the application of the force, the neutral axis is the one where the stress is zero. So at that axis, along any of the line, if you just take at any of the point in this neutral axis, the stress will be zero. Okay. At before and after the application, so the length CD or C dash D dash will be same since it is on the neutral axis. So that is called a theory of simple bending. So there are assumptions to derive the equations for bending or state the assumptions for bending stress or state Bernoulli's assumptions for beams bending. So these are the assumptions for for bending force. So the assumptions made to derive the bending force is the first one is the material of the beam is perfectly homogeneous and isotropic. Homogeneous in the sense if you consider along any of the section, the beam material is same throughout the section, throughout the length of the beam or any section, the property of the material is same since it is a homogeneous and isotropic. So that it states that is the first assumption. Second assumption, since it is homogeneous, we know that there is a Young's modulus for a material, it is a material property. So it remains same, whether it is in tension, whether this beam undergo tension is sags or hogs, the Young's modulus of the material will not change. Whether it is the top surface, if you consider here, it is in compression, the bottom surface is in tension. So any surface, if you consider the Young's modulus of a material will remain same. So that is the second assumption. The third assumption is transverse section remains plane before and after the bending moment is applied. So after the application of this moment, before it was a straighter beam. After the applying the moment, the beam has bent this manner. So that is, you can see there. If you're taking the section at this particular, at any of the point along the length, so this is one of the section, this is another section. Okay. So all these sections with respect to the neutral axis. So if you're going to take the section, these whatever the sections taken are parallels with respect to each other. So the section is not like this, whether it is not bent like this or it is not curved. So it is neither of it is right. The section is perpendicular with respect to the neutral axis. So at any point you are taking the section. That is the next assumption. So the fourth assumption is the beam is initially straight and it is unstressed. So before applying the load, the beam was initially it was a straighter beam and it is unstressed. There is no force or it is nothing is applying or any of the forces is not acting on the beam before the application of the moment. It is a complete straight beam. So that is the fourth assumption. So the fifth assumption is every cross section of the beam is symmetrical about the plane of bending about an axis perpendicular to it. So that is what it is explained already in third point. So that is if you take any of the section along the plane after it is bent, so all are symmetrical. So you have a symmetry between this plane to this plane. If you take the next plane, there is a symmetrical area you can get it between the planes. Next, the radius of curvature is large compared to depth of the beam. That is the last assumption. So that is, so this will be the depth of the beam. This will be depth of the beam. The radius of curvature will be very somewhere. It is sitting somewhere along. So if you can see there, this will be the radius center for the radius of curvature. So this length is larger. If you're taking to the inner fiber or outer fiber, so this length is large and compared to the thickness or depth of the beam. So that is the next assumption. So very important. I've asked this assumption somewhere for 4 marks. You need to write just 6 points. You can get easily 4 marks. It has been asked many times. Or along with the derivation, before starting the derivation, they will ask state the assumption and derive the bending force equation for the beam. Okay. So next we'll move on to the derivation, very important. So it has been asked many times. Okay. So this is the sketch for the derivation what we consider. So here, so let me, I'm not going to write it once again on the board. The same sketch we'll be using to derive. So we are considering the beam. So of a certain beam CD, ABCD is the beam that we consider. So ABCD is the beam which is straighter before applying the force. Before the application of the force, the beam was initially a straight beam and let NN be the neutral axis. This theory, what I'm saying, it has to be written by you. So kindly you can note down the sketch. I'll give you 3 minutes. So I can note down this sketch to derive. So we have considered a beam AB CD. So with NN is the neutral axis. To derive this, so we have considered a small portion. So this rectangular portion, what the line is indicating, small portion of elemental length EF. So inside this small portion, so this is the small portion which is considered. So of this small portion, this is the elemental length EF. So this elemental length EF is of width delta x, and it is at a distance y. The element what we considered EF, it is at a distance y from the neutral axis. It is at a distance y from neutral axis. Okay, this is before applying the force. So then after applying the force, so this is the sketch. After this is the small portion what we have considered. So this is this rectangle, and this width is delta x. So that is equal to EF. To derive the expression, we have considered a small portion of the beam. So after applying the force, so this whatever the portion that is C, that is A, B, C, D will change its position to A dash, C dash, B dash, and D dash. Okay. So that is the position of the points that is taken place after applying the moment. We are considered a beam which is going to sag, the sagging beam. So that is a top portion will be AC will be in compression, D will be in tension. And N dash is the position of the neutral axis. Since it is a neutral axis, the initial length of the neutral axis is NN, and the final length is N dash, both are same. Since there will be no stress at the neutral axis, NN will be equal to N dash. So whatever the portion we have considered EF, that is going to change to E dash, F dash. So this distance is Y. E dash is at a distance Y from the neutral axis. Okay, and neutral axis is at a distance R. Neutral axis is at a distance R. That is the radius of curvature. R from the center. Center of curvature, it is from R. Neutral axis is at a distance R, capital R. So this is after applying the moment. This is the stress distribution that is shown with respect to neutral axis. The top fibers. So this is the top fibers. It is going to undergo compression, whereas the bottom fibers. So these are the bottom fibers below the neutral axis. So these are undergoing tension. So that is shown with a. This is a stress graph. I think you have written the sketch. We'll start with the derivation. So for the stress diagram, you can show the arrow mark from this reference to right. You can put an arrow mark here. It has to be put. It is missing here. So at the bottom, it is from reference to left arrow mark direction. So you have written the sketch. So I'll be doing this on the board. The derivation to written. I'm not going to write the sketch again. The same sketch will be used. So this at the neutral axis, N, before applying the force, it was N, and after applying the force, it is N dash. So both are same. Since the stress is zero at the neutral axis, so this is the neutral axis. At neutral axis, stress is zero. The dimensions before and after applying, it is same. So this, the angle, it is a small deviation. So we'll use a sine rule. So this has to be like hypotenuse, the length from O to N dash, right? So it is theta will be equal to N N dash divided by O N. So we'll use that concept. So that is from the sketch. After bending, after applying the bending, the length N N will be equal to N dash N dash. So it is before applying the load and also after applying the force, right? This is before. At the neutral axis, since stress is 0, N N dash will be equal to, that is N N will be equal to N N dash. Since stress is 0 at the neutral axis, there will be no change in length. Okay? It is N dash, N N will be equal to N dash, N dash. So let me proceed with this. Okay? So next, from the figure, from the figure, from the figure, right? So let us, so this will be the straighter concept that we use of sine. Since angle is very small, let us consider this theta will be equal to, that is opposite. So this will be the hypotenuse for this. So this will be like a reference. So this n theta will be equal to n n dash divided by O n dash. So that is nothing but r. From the figure, theta is equal to n dash n divided by O n dash, that is equal to n dash divided by r. So n dash into n dash will be equal to r theta. N dash into n dash will be equal to r theta. So call this as equation 1. So similarly, so this is for neutral axis. Similarly, so this was the initial length for the small element what we are considering. The element is EF. The EF is going to change its position to E dash F dash. So by equation 1, this N dash is at distance R from O, whereas E dash F dash is at a distance. This, what is the distance for O to F? This is R plus Y. R plus Y. Therefore, I can write it for E dash F dash. Similarly, E dash F dash will be equal to R plus Y into theta. Call this as equation 2. Call this as equation 2. So now equation 2 minus equation 1. So you just subtract this, that is this n dash is the initial length, or n is the initial length of the beam before applying the load, before applying the moment, right? So whereas E dash F dash will get you the increase in length or change in length. It is a increase in length. N dash will get you the initial length. E dash will give you the, so since after applying the moment, this is going to be elongated. This is a E dash is increased, whereas EF is same as N dash, whereas E dash F dash is increased. It is increased in length. I need to find the change in length. To find the change in length, so the final length is E dash will get you the final length, whereas N dash will get you the N dash will get you the initial length. So the final length minus the initial length will get you the change in length. So I am going to subtract equation 2 by 1. So when you are subtracting 2 by 1, will get you a change in length for the beam. So that is equal to, so you just subtract this. So when you're subtracting, so theta into r will get cancelled. So we'll be remaining with, I'll be writing directly, I think y theta. Y theta is the change in length or increase in length, change in length or increase in length. So next, you know that definition for the strain. Strain is given by, strain for a material, it is given by epsilon. Strain is given by epsilon. What is the equation? Strain is defined as what? Strain is defined as change in length,
The original length.
original length, original length. So we know that change in length we have found, change in length is y theta. So it will be, write it here. So that is epsilon is equal to, E is equal to, change in length is y theta, original length is r theta by equation 1. So it is r theta. So theta theta gets cancelled. E will be equal to y by r. This strain will be equal to y by r. We call this as equation, next equation. So that is equation 3. Next, we know by Hooke's law. By Hooke's law, by Hooke's law, the stress is defined as what? Stress is equal to, by Hooke's law, stress is defined as what? Stress is equal to, stress proportional to strain. What is the proportionality? Stress is equal to E into E, right? E is Young's modulus. E is the strain. Greek symbol E is the strain, right? This is by Hooke's law. So make use of this. So we are going to make use of this. So Young's modulus. So by equation 3, you just substitute by equation 3. E is given by y by r. Therefore, sigma will be equal to y by r into E. Or you just rearrange, sigma by y will be equal to E by r. Call this as equation 4. Sigma by y is equal to E by r. So this is half of the derivation where E and R are constants. So you can write where E and R are constants. So hence the stress in a layer is proportional to, so since E and R are constants, the stress in a layer is proportional to distance from neutral axis. So this is one half of the derivation is completed. That is stress at any layer, is proportional to, it is the distance from neutral axis. Okay. So that is the beam is compression, the bottom portion is in tension. So now let us consider, a small portion, a small element. So if this is the, beam, what we have considered, and it is the neutral axis. This is the neutral axis. So now let us consider a very small portion which is, so now consider a small element. So this sentence has to be written by you. So let us consider a small element dy at a distance y from the neutral axis, and area of the element is a. sorry, dA, and dA be the dA be the area of the element dy. So now we know that force is given by what? With respect to the stress, the force. So let us find the force acting on this layer, the force on the element. So that is equal to, force is equal to what? Stress into area, right? So stress into area. So let us take the stress is sigma and area it is dA. Area let it be dA. Force on this element considered is sigma into dA. So from equation 4, you can write it for sigma, equation for sigma. So from 4, so this force acting on the element that will be equal to y into E by R into dA. Right? So this is the force acting on this element at the layer. So now, so moment of this force about neutral axis. The moment, what is the moment of this force for the element dy about the neutral axis, about the neutral axis. So what is moment? Moment is a force into distance, right? So what is that force that is acting on the moment? What is that for? What is that moment for this force which is acting on the element? So what should be the moment? So it is how much? The moment acting on this element considered. It is F into y, right? The moment of the force, so that is equal to F into, so since the distance for this element is y, it is F into y. So that is equal to F into, F is what? F is this quantity. So by the above equation, F is y into, so y into y, it will be y square. I'll be writing directly. So it is E by R, y into y square dA. Okay. So this is for a single element. So this is for a single element at what we have considered for entire beam. So in the entire beam, there will be number of elements here. There will be number of elements throughout the cross section. If you consider, there will be number of layers that will be present for a beam. So you need to consider all these elements which are present inside this depth of the beam. So each layer will be at certain distance. Okay. So this is for a single layer. So I need to consider for all the elements which are present inside the beam. So the total moment, total moment. So that we call it as total moment of all the elements which are present. So there will be number of layer by layer with respect to neutral axis, right? With respect to neutral axis, the total moment of all the element with respect to neutral axis, we call that as moment of resistance. We call that as a moment of resistance or a total moment that is equal to integral of, so when integral or sum of all the moments, in some books it will be using sum of or integral of this above quantity, integral of, we are considered for single layer. So it is, I need to consider for all the layers from 0 to L distance, thickness, if I want to take. So I need to consider for, I need to consider it for each and every layer. So I am going to add it, or I'm going to take all the length. So that is, we are going to integrate this above equation to get the moment or a total moment. So that is integral of this above moment, or the sum of all the above moment will get you the total moment that is acting with respect to the total depth of the beam. So this quantity, so this is equal to E by R. E by R is constant. E by R is constant. E by R into integral of y square dA, right? So this y square dA, this y square dA, this is, we call it as, or integral of y square dA is called moment of inertia. Moment of inertia. That is, dA is moment of area into moment of area. That is moment of inertia. It is y square. Illi y square is illi area. dA is also, the unit for dA is what? Area is meter square. If it is meter, if it is meter square. Y is also a distance. It is a length. Since it is y square, you will get meter square only. So that meter square into meter square, the unit for moment of inertia, it is meter to the power of 4 or length to the power of 4. Okay, this term we call it as y square dA, integral of y square dA as moment of inertia, and it is denoted by I, capital I. So you substitute this as I in the above equation. So this total moment is given by M. Total moment is given by capital M. So M is equal to E by R into I. Or you just rearrange, M by I will be equal to E by R. Call this as equation 3, 4, 5. Call this as equation 5. Compare now equation 4 with 5. By 4 and 5, I can write M by I is equal to sigma by Y is equal to E by R. Okay, this is the bending equation, equation 6, bending equation or bending stress equation for a beam. Equation 6 is the bending stress equation for a beam. I is moment of inertia. So it is moment of inertia is nothing but a moment of area about all the moment of area of all the layers with respect to neutral axis. Respect to neutral axis. That we call it as a moment of inertia. So and its unit is, it is mm power 4 or meter power 4. Since it is y square dA, dA is a meter square. It is area into meter square. It will be meter square or mm to the power of 4. This is the derivation. It has been asked almost all the papers. And problems on this, you need to remember this equation. So either you will be using these two combination or any of the combination, these two or these two or these two. So any it can be written for moment. The moment can be given as sigma by y by I. So this can we call it as Z. Z is equal to y by I or c by I. It is called as a section modulus. It depends on type of cross section. If it is rectangle, the moment of inertia is changed. If it is circular, there are different equations. We'll tell in while solving the problems. Okay. So this term we call it as a section modulus. So we'll stop